Welcome everybody. Today we're going to be looking at lesson 5, special factoring cases. The first one we're going to look at is a perfect square trinomial. But again, let's work backwards and use what we know in our previous unit of polynomials and expand this expression right here. So we have 2x plus 3 squared, and that just means 2x plus 3 times 2x plus 3. So when I expand that or FOIL, I'm going to get 4x squared plus 12x plus 9. Okay, now if I had to go from here back to my original factored expression, I might apply my factoring techniques that we learned last lesson. But it might take you some time, especially if you're not confident factoring trinomials with a leading coefficient yet. So there is a bit of a shortcut here, and there's a hint that this expression here gives us, and that is, I rewrote it down here, and that is that both the first and the last term are perfect squares, and hence this is why this case is called perfect square trinomials. So if that is the case, if you do have, obviously the x squared here has to be a perfect square as well. If that is the case, in other words, that I have my first and last term as perfect squares, then there is a shortcut to this, and that is to, again, start with your brackets, take the square root of each of those terms. So the square root of 4x squared is 2x, and write that as the first term in each binomial. The square root of 9 is 3 plus 3 plus 3. So this, again, you always want to double check, because this might not always work out. Most of the time it will work out if your first and last term are perfect squares, but do check. And because I can just look up here to see that that is indeed what we started with. Let's do another example, get the hang of this. So again, double check to see, well, first always check to see if you can take out a greatest common factor. In this case I can't, and if I look at my leading coefficient, it's 16, and if I were to try and do this using what we did last class, it might take me some time, but again, there's that sort of hint that this question gives you, and that is that the first and the last term are perfect squares. So I'm going to take the square root of each of those, so 16x squared and 25 to get 4x and 5 here, and then when I do my two brackets, I'm just going to go and place each of those answers here, 4x, and then plus 5 plus 5. Again, double check your answer. I didn't do this, I didn't expand this one right from the beginning, so I will check this one. So I will FOIL this, and let's see what happens. So we'll go first to get 16x squared. Okay, that's good. And then outside, 4x times 5 to get 20x. And then I'm going to do the inside to get plus 20x, and then the last here to get plus 25, and then when I combine my like terms, I should get 16x squared plus 40x plus 25. And many of you are probably noticing alarm bells are going off right now, saying, oh, wait a minute, we have plus 40x, but the original question had a minus 40x. So what happened there, and where did we go wrong? Well, here's the answer. The square root of 25 here can also be negative 5, because negative 5 squared gives us 25. So I could have had as a correct answer negative 5 and negative 5. And whenever you see that your middle term is a negative number, then that is most likely going to be the answer. Actually, I should say always going to be the answer. you take a negative version of the square root of the last term. Let's try this. So if I were to FOIL this now, I would get, instead of these positives, that should have been a 20 there, I'll rewrite it. Instead of the positive 20 now, I should get a negative 20x minus 20x. And then down here, when I combine those like terms, I should get a negative 40x. Okay, so check that. That is what we started with, so that is how to do that one. Okay, now moving on to another special case here, the second case we're going to do, and that's called the difference of squares. And we'll see why in a second, why that's called that way. But let's go ahead and work backwards and expand this expression down here. So we have two binomials multiplying. I'll FOIL this, and I'm going to get x squared as the first, and then minus 7x, and I'll do the inside plus 7x, and then finally last minus 49. I'll combine my like terms, which are the two in the middle, to get x squared, and negative 7x plus 7x gives me a 0, so the middle term actually disappears. I don't have to write it. And my answer is x squared minus 49. But now, how do we take that x squared minus 49 and go back and factor it and end up with the original two binomials here? Well, here is again a little hint that this one is easier to see, the difference of squares. It's easier to see than the perfect square trinomials because you are starting off with a binomial. You're starting off with two terms, 1, 2. And here's what you're looking for. You're looking to see that both of those terms are perfect squares. And yes, they are. X squared is a perfect square, and so is 49. So that's the first check. So I can maybe put here check number 1 to see if they're both perfect squares. And then the second thing you have to check for, the second thing, check 2 here, you have to check for that negative sign in between the two terms. In other words, we're looking for the difference between the first and the second term, and that's why it's called the difference of squares. Okay, if that is the case, and you give yourself 2 check marks there, then you can go ahead and do a little, again, bracket, and take the square root of the first term, which is the square root of x to get, square root of x squared to get x, the square root of 49 to get 7. So but here is the only difference from the perfect square trinomials above, is that the signs are going to be different. So we're going to have a positive and a negative. So it's going to be x plus 7 and x minus 7. And that this is why, because the signs are different, that's why we get the opposite two middle terms here, negative 7 and plus 7. And that's why they eliminate each other, and the middle term in the trinomial is gone, and it becomes a binomial. Let's do another example here. Okay. Do your checks. Okay, I have two perfect squares, 9x squared and 25, and there is a difference here, a minus sign between them, so I can use this perfect square, difference of squares method. So I'll start with my brackets, and I'll take the square root of 9x squared to get 3x. I'll put the 3x here in the beginning of both binomials. Then I'll do the same thing to the 25. I'll get a 5, put the 5 down. And then again, your signs are going to be a plus and a minus. That you can change. It doesn't have to. The order doesn't matter here. It can be a 3x minus 5, 3x plus 5. Let's, however, check this one. So because I didn't start off with the with the expanded version. So really quickly, I'll FOIL this, and hopefully we end up with what we started up here. So first we have 3x times 3x, 9x squared. Outside, 3x minus 5 is negative 15x, and then we'll do the inside to get positive 15x, and I can already see that those two are going to cancel each other out. And then I'll finish it off here. 5 times negative 5 is minus 25. So these two here are going to give me a 0, 0x, whatever you want to call it, but I don't have to write it. So I'm really just left with 9x squared minus 25. That is what we started with up here. Okay, thank you for watching, and see you next time.